Uh, my name is Atayr Brian from Group 32, and we're going to take you through feature extraction. Yes, so I'm going to begin by we begin with understanding feature extraction. Feature extraction is a machine learning technique that reduces the number of resources required for processing while retaining significant or relevant information. Yes, we can think of feature extraction. We can think of feature extraction as a way of simplifying a data set by picking out the most important parts that are going to be valuable to our project or to our model, and then leaving out the least important ones. Yes, in this way, we shall be able to avoid the redundant information that comes along with the complexity of data sets, because we know machine learning data sets, they often have a lot of complex things, a lot of information. And in most cases, we don't really need all the information. We don't really need all the information. So feature extraction comes in as an aid to help us get rid of what we don't really need that much, and then focus on what we need the very most. Yes, feature extraction has benefits. Of course, it has very many benefits, but we listed a few and we are going to talk about them. I will begin with reduced computational costs. This is because it's very normal and it's common knowledge that handling 10,000 pixels of an image is much harder and computationally costly compared to handling 1,000 pixels of information of an image. So like if you have an image of 10,000 pixels and then you extract out the most important features and they make up to about 1,000, yeah, I think the computational costs will significantly reduce. Yes, the next one is improving model performance, and this is on the lines of accuracy. It's because after feature extraction, we reduce the noise, we reduce the noises, and then yes, the model it becomes very accurate. Then it also gets better insights because we know that algorithms work better with not limited information, but with specific information picked out. They work better with unique information picked out. Yes, so it gets better insights, and then yeah, it also prevents overfitting. It also prevents overfitting. Uh, Moving on, there are different types of techniques for feature extraction. Yes, there are very many different types of techniques used in feature extraction, and we are going to talk about them. We begin with the statistical methods. The statistical methods, these are the normal methods we know, the mean, the median, standard deviation, correlation, covariance. Yes, these statistical methods are widely used in feature extraction to summarize and explain patterns of data. So the statistical methods are mainly used to establish spreads, to establish links between the information, and then also to represent like the trends, the center. Yes, that's the main purpose of the statistical methods. And yes, they are the normal ones. The definition are the normal ones: mean, average, median, the middle number after organizing the data in descending or ascending order, standard deviation. Yeah, they are really the same definitions. Then number two, we go to dimensionality reduction methods for feature extraction. Dimensionality reduction, this simply means reducing reducing complex data from high dimension to lower dimensions for easy interpretability. Yes, and dimensionality reduction can be done in very many ways, We have the principal component analysis, the PCA. We have the linear discriminant analysis, LDA. We have the independent component analysis. We have the autoencoders. We have the TSNE. Yeah, we have very many, and we are going to talk about each of them, beginning with the principal component analysis. Yes, the PCA, I think, define the PCA as simply reducing the number of features while maintaining the key ones, so in maintaining the important ones. Yes. You capture those with I think the most importance. Yes, we capture those with the most importance, and we leave out those that we don't really need. That's mostly like the principal component analysis. Then we go to the LD, the linear discriminant analysis. Linear discriminant analysis, yes, it's so a dimensionality reduction method technique. It reduces the dimensions, but then now the LD focuses on separating classes of the data, the different classes of the data. Yes, it reduces the dimensions, but then its sole focus is actually to maximize the separation between the different classes of the data in a data set. No, to maximize the separation between the different classes of the data in a data set. That's more of, that's LDA. Then autoencoders. Autoencoders are neural networks that learn to optimize or learn to compress the data and then later decompress it when needed, like the encode and then decode. Yes, they encode the data and then later decode it. In this way, they're able to minimize the information and actually pick out the most important information. Yes, we go to the T-distributed stochastic neighbor embedding. Yes, the TSNE, yes, it's a nonlinear dimensional reduction technique. Yes, and then for it, it reduces the, of course, it reduces the dimensions, but then it mostly preserves the relationships between the different data points. Yes, that's like, so the simple definition can be the T-distributed stochastic neighbor embedding. Yes, it also minimizes or it reduces the dimension of the data, but then it makes sure it preserves the relationships or the patterns between the different data points. Then we go to the independent component analysis. You see, data is, it's always made up of a mixture of very many different components. Yes, because the word data is broad and wide, but then data is always made up of different components mixed all together to come up with whatever raw data they actually come up with. So the main goal of the ICA, the independent component analysis, is to separate this data, break down the components. Yes, more of unmixing it. You know, if it's like a mixture of different components, it's the ICA unmixes it. Yes. Then we go to the third type. We have feature extraction methods for textual data. Yes. Here we have the bag of words and then the term frequency inverse document frequency. Yes, the bag of words. I can simply explain this one. I can explain it in a way that it organizes, it actually goes, or it iterates through a document and picks out the unique words, then creates a collection of those unique words and how often the words actually appear. Yes, it will go through your document, then it will pick out the unique words and then how often the unique words appear. So like these ones, they represent textual data into a set of numerical values. Yes, so it will go through the document and then pick out the unique words and how often they actually appear. Then the term frequency inverse document frequency. This also works as bag of words because it also goes through a document, then it picks out how often the unique words appear. But the only difference is that the TF IDF, now for it, it goes ahead and adds weights. It adds weights of importance to the unique words that are extracted. Yes, that is the weights of importance. So yes, it's going to pick out the unique words, how often they appear. This is the term frequency. And then the inverse document frequency, how often they appear across the documents. Like it matches with the importance, it attaches weights, it attaches the weights of importance to the words. Yes, the fourth type, we have the signal processing methods. We have the Fourier transform and then the wavelet transform is the Fourier transform. It converts a signal from its original domain to a representation in the frequency. Yes, what the Fourier transform simply does is signals are made up of very many different frequencies. Yeah, so what the Fourier transform will do is it's going to break down the signals into, the signal into the different frequency components. Yes. An example I can use here is, imagine you're listening to an orchestra, and yes, they're playing music, they're playing nice music, and you see in an orchestra, they use different instruments. They use different instruments to come up with that nice sound. So what happens here is, what the Fourier transform will do is going to break down that sound, that music, that fine melody that is playing, and it's going to break down into the components. It's going to tell you that this note is from the guitar, this note is from the trumpet, this note is from the flute. Yes, it's going to show you all those. It's going to break down those notes, the frequencies, into those different components. Yes. And then now when you come to the wavelet transformation or wavelet transform, it works as the Fourier transform because it's also going to break down the frequency into the different components. But then now the wavelet transform, it keeps track of time and then location. Yes, it preserves the time and location. So the analogy I can use, or the example I can use here is that imagine you're watching a movie and then there is a background song playing. So normally what the Fourier transform will do is with that background song, it's going to tell you that note is for the guitar, that note is for the flute, that's for the trumpet. Yes, it's going to break that down like the way we had seen. But then now the wavelet transform will attach time and location. So the wavelet transform will tell you that note is from the guitar and it plays from this minute to this minute. That note is from the trumpet and it plays for this time to this time. Yes, that's the difference between the wavelet transform and then the Fourier transform. But at the end of the day, they'll all pick out the most important information from the signal, other than having the entire thing. It's going to tell you that this is for this. Yes. And in that way, we shall be able to pick out the important parts. Then we have image data construction. Image data construction. Yes, the image data construction, the image data extraction, excuse me. Yes, we have, of course, the histogram-oriented graphs. We have the scale invariant feature transform. Then we have the convolutional, CNN features. So the HOG, this mainly focuses on the shapes and edges of an image. Yes, it only focuses on the shapes and edges of an image. And the SIFT also, it extracts the distinctive features or the key parts of an image, but then, yes, it extracts the key parts of an image and but then the one thing we can note about the SIFT is that it's scale invariant. If the image is resized or rotated, it's going to give you the same information. It's going to give you the same information. It's not going to change. The output will be the same. Then the CNN features, of course, these ones, unlike in SIFT and then HOG, this one are the CNN features. They learn to pick the high level features on their own. They really learn to think the high level features on their own. Yes, so how do we know that this is the right method to use? Of course, that depends on the user and of course the very many factors that come into play. But then of course you have to note things that feature extraction comes along with information loss Yes, and of course it comes along with computational complexity. Yes, that's all I had. Thank you so much. My colleague is going to take you through the following bits about feature extraction. Thank you so much.
Hello everyone and welcome to this presentation on feature extraction, and my name is Habao Simon, and in this video I'll be talking about the application of feature extraction. Without further ado, let's dive in. So the applications of feature extraction, we'll focus on majorly 4 key areas: natural language processing, image processing, and computer vision, then biometric authentication, then signal processing and audio analysis. In natural language processing, we are extracting features from text to categorize documents, analyze speech by recognizing different types of speech. Then in image processing and computer vision, we're identifying objects, detecting faces, and categorizing images. Then in biometric authentication, using features like fingerprints, iris, and also voice prints for security. Then in signal processing, we are extracting features from audio signals for tasks like music genre classification or health monitoring. So to dive into natural language processing, this one heavily focuses on feature extraction to make sense of text data. And here we have document categorization. Here extracting characteristics from text data to sort documents or text into specific categories. Features like let me say like word frequency help to classify documents into categories such as spam or not spam. Basically, if you're working with emails or something. Then in emotion analysis, determining the feelings or sentiments conveyed in text by identifying relevant features. By extracting these sentiment-related features, we can determine whether a text conveys happiness or sadness. Then in speech recognition, features like the MFCCs, mostly known as MEL frequency, what septro coefficients are extracted from audio signals to identify spoken words. Then image processing and computer vision. Here, feature extraction helps machines see and interpret images. An example here, we have object detection, extracting features like edges, textures, or shapes to identify objects in images. Here is what happens. Then facial detection. Here we are recognizing faces by extracting those facial landmarks such as eyes, structure of the mouth, and structure maybe of like the nose. Then image categorization. This basically deals with grouping images into classes like, let's say, working with animal data set, you have cats versus dogs. Using features extracted by the CNNs, you can be able to categorize these images. Then signal processing and audio analysis. Here, feature extraction plays a vital role in understanding the audio signals. For instance, the music genre classification, here we have features like pitch, rhythm, and spectral contrast that help classify songs into genres. This is how like Spotify was built based on like these recommendations from this audio analysis. Then speaker identification. This is basically used to like identify voice and match it to like a certain person. Here we use voice prints and MFCCs, like I earlier said, are used to authenticate users in banking or security systems. Then biomedical signal processing features like ECG, EEG signals, features from these ECG and EEG signals help detect what we call what heart arrhythmias or analyze brain activity for basically those dealing with neuroscience. Then tools and libraries used for feature extraction, we have scikit-learn, OpenCV, TensorFlow. So what does scikit-learn do? This is a Python library that offers tools like PCA, which is known as Principal Component Analysis, for dimensionality reduction, and the TF-IDF for text feature extraction. Yeah. Then OpenCV, it's a computer vision library with functions for extracting images, extracting image features such as SFIT, SAF, and ORB. Then we have TensorFlow. It's a deep learning framework that automates feature extraction using neural networks. Then a continuation, we have PyTorch and also Librosa. So PyTorch is has no difference between this TensorFlow that I had earlier said. It's also a deep learning framework that allows feature extraction using, of course, the neural network architectures. Then we have Librosa. This is specifically for audio analysis, providing tools like extract features, provides tools to extract features like the MFCCs earlier said. Then advantages of feature extraction. One, it simplifies the data complexity by doing dimensionality reduction. Feature extraction makes data easier to visualize and analyze once you've performed the PCA, of course. Then we have enhanced machine learning performance, extracting features, relevant features here, improves model accuracy and reduces overfitting. Then streamlined data analysis, focusing on key elements, saves time, of course, and computational resources, leaving out those that are not required really, or that are insignificant, if I'm to say. Then challenges in achieving feature extraction. If you're dealing with high dimensional data, then, for example, data sets with a lot of features can lead to like the curse of dimensionality, where data becomes sparse and distances lose meaning. This can reduce the model accuracy, of course. Then we have overfitting and underfitting. When you extract too many features, this can cause overfitting, while if you extract too few features, then it can lead to underfitting. So which means balancing is very crucial in this case. Then computational complexity, extracting features from large datasets can be time and resource intensive, especially when you're dealing with high resolution images or audio signals or high resolution videos. This can lead to like high computation, can require high computation power. Then implementations, we have to look at some code here. We see, for example, feature extraction for audio. This is extracting the MFCCs earlier talked about, male frequency spectral coefficients. So here we use Librosa, the library I had talked about before. Then we can extract the MFCCs from an audio file by loading it, of course. These coefficients capture the spectral characteristics of sound, useful for tasks like speech recognition. One example of where the feature extraction is applied, then we have text feature extraction using the scikit-learn's what's it called? TF-ID vectorizer. We can convert text into numerical features, enabling document classification or sentiment analysis. Then this is basically the code to do that. Then action for time series, you're using Fourier transform library from NumPy. We have to first import, of course, NumPy. Then from there, we can import this Fourier transform. We can analyze the frequency components or a signal, which is essential in fields like biomedical signal processing. Basically, a sample code to do that. So in conclusion, feature extraction is, of course, a powerful technique that transforms raw data into meaningful features. This enables machines to learn and make decisions. From natural language processing and computer vision to audio analysis, its applications are very many and, of course, impactful. Thank you.